Hello everyone. So today we are going to do Leetcode daily challenge validates binary search tree. So now in this question, let's first understand that what a binary search tree is and how this question goes on for validating. Okay. So here comes the part that what it exactly is saying. That given the root, 1 minute. So given the root of binary tree, determine if it is a valid binary search tree. This we need to figure out. Now here comes the part. A valid binary search tree is defined as the left subtree of a node contains only nodes with keys less than node key, and the right subtree of node contains only nodes which are greater than the node key. And both left and right subtree must also be binary search tree. So this is how a valid binary search tree would be. Means all according to the properties of a binary search tree only. Means left should be less than the root and should be less than the right. So this is the thing which we are required to check here. So now comes the part that how we are required to do this and what would be the approach for this particular. So see, the thing which we are required, we would be given with this particular tree would be given, right? So what we can do is we are having two methods to do the same. Either we can do iteratively using our DFS, or we can do by DFS. But I would preferably say you to use a DFS, because in that we would be easily able to recursively check for both of the subtrees. So if we are going to go ahead with DFS, the thing would be when we go to this particular node, right? Because in the DFS, what we would be doing is that we would be going to this 2, and then after that this 1 would be there, and then after that this 3. How all this would be done? Then we go ahead with the left, right, in our DFS. Then we will check that if this left is greater than or less than this particular node, which is at this node, right? So the thing would be, if our left node is basically greater than this particular, then we'll return false. And when we return false, then this call would be returned to its parent caller, that is this one. And then when it comes to this particular part, now it will check that is there any other call which is left, then yes. The other call, that is this one which is left, so it will go to this, and then it will check that is it greater than or less than my this node. So if it would have been less than, then it will return false here, and then from there only it will exit. But now here the case is opposite, that it is already a valid tree, right? So in that scenario, then it goes here, it will return true to this particular, and then it will check for its right one, and here also it will return true, and at the end true would be returned. So this is how the DFS would have been done. Now comes the part that how we are required to go ahead with the DFS solution. So DFS is basically recursion by heart. If we do it by recursive method, then because DFS could also be done using stacks, and that would be iterative method. But if we want to use the recursive stacks, that is the stacks which are provided by which are inbuilt, helping us doing the recursion. So for that fact, how we need to come up, we need to check for the base case options which we are having, and need to come up with a recurrence relation which would be valid for this particular question. So these are the 3 things which we would be required for doing our DFS. So these things you need to think. Now before coming to base case, we need to check that what options we are having. So basically in a binary search tree, means in a binary tree, we have only 2 options. Either we can go to this side or we can go to this side, right? So that's why we are having 2 options, that is going towards left and going towards right. And on the basis of that only we will be checking that is our present node, that is this particular node, is it less than our left node or greater than our left node. basically if our this particular is greater than our left node, then this is a valid condition, because in a binary search tree we always require left, then root, and then right. So that's why this condition would be true. But if this is the scenario, then we'll directly return false. So this is the thing which we need to keep a check on. Now at the next portion, so now this is for the left one, and now for the right one, we again need to check that if this particular is greater than the right one, then it will return false. But if it is less than the right node, then it will return true. So these are the options, and according to which we will be deriving our recurrence relation. Now comes the part that how we would be doing so. So for creating a recurrence relation, we would be only checking for the fact that if our left one is basically greater than our present node, or means here what I was trying to do was that I was going ahead with the reverse condition, that if it is if our left is greater than present node, or if our right is less than present node, then at that way only it will return false, so that it could easily exit out from our recursive stack. That's the thing. And then at the end, what we will be checking is, that if any of the call returns false, then we would be returning that thing to our main caller function, and after that our main caller function will return that particular as our answer. So that was the thing which we can do. Means a recurrence relation would be something like this, that our function is there, and in that we will be checking for min node, then our root node. Means these are our parameters which we'll be taking for a recurrence relation. And after that we will be going ahead that how we will be moving ahead in the same. So for that, what we will be doing is, first thing is that condition, that if it is greater than or if it is less than, so according to that we will be returning false, and at the end we will be checking that if any one of them, or what is the result that both of them are returning. So according to that we will be returning to our main caller function, and then we will be moving ahead. So let us just code this particular, and then we will check that what exactly I was saying. So here we are given with this particular function, right? So now as here we are just given with one root node, but we require basically checking for left node also and right node also, right? So for that we will be making a new recursive function. So, and it's important that we declare everything inside a private, so that means whenever the functions are global, or even a variable is global, so it's you cannot it is although not mandatory, but it is a good practice to keep it as a private function or a private global variable, so that it is only accessible by this class. So now comes the part that how our function would be. So we will be returning true or false, so that's why we are taking the return type as boolean, and then we require the chapter. So we require basically one is the min node which we will require, and then our root node which we require, and then our max node which we require. So these are the parameters which we will be passing in the same. And then comes the part that how we will be going ahead with our recurrence relation, our base case, and what at the end we will be returning. So now comes the part that what would be the base case according to the recurrence relation which we were deriving, right? So first let us write that how a function will proceed. So first thing which we will be checking is that if the min node is there and if our min node, because it is a node, right? So we need to check for its value for comparison with our root node's value. If that is the scene, I'm checking for the reverse one. So if that is the scene, then at this condition we are required to return false, because the left subtree should be a smaller node having the all the nodes which should be smaller than our root. And now comes the part for the max node, that it should exist, and if it exists then we need to check that our max node value, that should be basically less than or equals to root value. So this is the thing which we will be checking. And if in these scenario, like if min node exists and then if its value is basically greater than root, or if max node exists and its value is less than root value, then in that scenario we will be directly returning false. So this is the way how our function will be behaving. Now comes the part that how we will be returning. So if we want to return, so we need to check that whenever this in our function we are coming to this particular line, so how it would be behaving, right? So we need to check, we need to call out this particular function again and again according to modification of our min node and max node. That is the thing which we will be doing. So now we will be calling our function and returning to our parent caller. By this means we will be first checking the min node as it is, and then we are required to give our root node the value of left, and at this moment it will be checking, and then we also need to check for the right subtree also, right? So that's why now we will be do modification for our right subtree. So here we will be giving the root in our min node, and then root's right would be given, and then max node would remain as it is. So this is the thing which we will be returning. So when checking for the left subtree, that is making root equals to root left, then min node remain as it is, as that is the limit set for the left subtree. But the max node changes to present root value as upper limit is required to be changed. So that is the thing which we are doing in this particular call when we are checking for left subtree, and for when we are checking for right subtree. So these are the things which we are checking. Now comes the part that we are done with, that how our function will proceed and what should be the return statement. But there is one thing missing, that is our base case. So just think that how our base case would be. In most of the binary tree, one mandatory base case is that if root doesn't exist, then we need to do something, right? So here also that is one of the mandatory base case. But anything else, I don't think so there is any other condition which is required to done means, or any other edge case, because we have already covered up that if it exists then only we need to check, or if this exists then only we need to check. So this is already covered, and we are checking for left subtree and for right subtree. So now comes the part that if our root doesn't exist, then we will be returning true. And why we are returning true? Because a null node is in itself a complete binary search tree. That's why. So now comes the part that this was the function which we wrote, right? So we need to call this function also, right? So here we will be calling this function. We'll directly write that we need to here check we'll call this return to check function, and at the starting we will be passing null and then root and then null. At the starting we will be going ahead like this, so that we could move ahead in our function. So this was all for this particular question. Now comes the part of time complexity and space complexity. So the time complexity for this particular question is order of n at the worst case scenario, because it could also be a skew tree, right? So when it becomes a skew tree as per this particular, so if it becomes a skew tree, right, so then it will be completely order of n. And if it is not a skew tree, then in that scenario, it will be order of log n only. So we always take the time complexity for the worst case scenario. So that's why time complexity is order of n. That is all the nodes which are present there, and if they are completely in a skew manner. And the space complexity here would be directly, if we say that we are not considering the recursive stack, then it is order of 1, and if we are considering the recursive stack, then again it is order of n, and n here is simply the number of nodes. So this was all for this question. If you have any doubts, then you could comment that down. So yeah, thank you.